Hey everybody, so let's get started with a new topic, magnetism. We're gonna break out of DC circuits, and if we have some time, we'll get back into some circuit analysis with especially the AC circuit, because as there was a circuit element that depended on charge and electric fields, which is called the capacitor. So there is a circuit element that depends on the magnetism, and it is called the inductor. So if we have time at the end, um, we can take a quick look at some AC circuits and the responses of capacitors and inductors to an AC signal. But in the meantime, let's get started with some magnetism. This is going to start kind of in the same vein as the electric. We started the electrical part. We started the electrical part with electrostatics, meaning that none of the charges were moving, and we were simply analyzing only the static case with the electric fields. So now, in order to get magnetostatics, we can't quite call it a static case, but it's maybe a time a non-time varying case, a time independent case, perhaps. So let's get started. I'll show you what I'm talking about here. Okay, so we'll start with magnetism. I'm going to start with the magnetic field of Earth, because that's kind of how magnetism essentially started, ultimately. And people have known about the magnetic field for 5,000 years. Essentially, it's been something that's been studied and thought about and gotten wrong plenty of times. Unfortunately, we've got Maxwell's equations now. So we've got to interpret what we've got with Maxwell's equations and try to make it fit with what we're seeing. So after that, we're going to go into domains, which is how magnetism works in a material. After that, we'll go even further in and talk about how domains are formed in a material with the in the atoms themselves. And then finally, we'll back up all the way to kind of approximately where we started with macroscopic magnetic forces and torques. All right, so we'll see how we go with this. Might take a couple of videos. I mean, it will take a couple of videos to get through this stuff. But point is, we'll get started on it. So let's get going. So the magnetic field of Earth. Well, first of all, let's draw a magnetic field. Let's start by drawing. We kind of we started off a little bit with drawing of the electric field. So let's draw the magnetic fields. If you have ever seen one of those demonstrations with a magnet and some iron filings, or a liquid that has some iron bits in it, then you'll know kind of what I'm about to draw. It looks very similar to something we've already dealt with electrically. If you haven't seen those, I'll try to dig up something on YouTube, or maybe I'll even take a few pictures. I'll go when I go into lab next. So for example, here's a bar magnet. Try to draw the simplest one. Don't look at a refrigerator magnet, not yet. Those are not straightforward. So here's a bar magnet. What we find is that when we take it and put it near a bucket with iron filings in it, the iron filings kind of line up in this pattern. Whoops. I want that. There we go. You get the idea. I think that one was not quite good. A little better? Okay, yep. Okay. So we find that there are two ends to each magnet. And incidentally, each magnet has two ends, which is a bit of a funny thing to say, but you all, in other words, when you look at the field, it's always nearly kind of like it's like it's coming out from one side, right? But it's also coming out from the other side. Now, the reason I put magnets have two ends is because charges don't. Charges, you have a positive charge and it just comes out. There's no, right? There's no going back in unless you put a negative charge somewhere nearby, right? So the magnets always have an in and an out. So in other words, what we would have said is that they're always dipole-ish, okay? Now, this is exactly what Earth's field looks like. At least it's good to a first approximation. All magnets are dipoles. It's good to a first approximation. So if we take a look at this field here and I say, okay, what does Earth field look like? Well, Earth has a field, in case you weren't aware of that. Okay. Here's your spin axis. This is the north geographic pole. Here's the south, right? This is down with Antarctica down here. Let's see. I can try doing something here. All right, so okay, so somewhere like around, so this is obviously North America here, South America there. Iceland, Greenland's kind of over here on the very side. The UK is over there. Here is Siberia over near Alaska, and Philippines, Japan. Here's the end of Australia right in here. The reason I draw this is because if you have a compass, it points north, which is pretty groovy. It tells you north. In other words, if you take a look at your compass and you say, oh, I've got a needle here, typically one side of your needle is red like that. And then the other side just looks kind of like that. And so your red side is the north pointing side, okay? And it's been known about for a really long time, like I said, 5,000 years, that if you took a particular type of stone called lodestone and you hung it from a thread, or you somehow balanced it in water where it was buoyant, put some leaves underneath it or something like that, it would rotate until one end of it was pointing north and the other end was pointing south. And ultimately, that's the basis of the compass. It was not well known exactly why that happened. So certainly, since the part that was pointing north is telling you which way it is to the North Pole, that side is called the north side of the magnet. So this side here is the north side of the magnet, and this side here is the south side of the magnet. So magnets do not actually, they're not called charges. When we talk about electrical things, we say, oh, we have electric charges. We do not have magnetic charges. We have magnetic poles. Okay, so the terminology is a little bit different. And we have a north and a south pole, and this is why. Okay, so the north part of the magnet points to north. Now, if you look at Earth's field, then what Earth's field does is it does something approximately like this. Let's see. Huh. Well, that's kind of funny, isn't it? It's like if you were up here, right? These lines are all kind of coming down over here. If you were up here wandering around in northern Canada and you used a magnet, it looks to me like the north side of the magnet might actually be pointed that way, thus making your compass not very useful, at least in a geographic sense. It's working terrifically well magnetically. It turns out the magnetic pole is actually offset from the rotational axis of Earth by about 11 degrees. Um, and that the pole up here, the magnetic pole up here in the northern hemisphere, is located somewhere up in northern Canada, and the south pole is located somewhere off the coast of Chile, I believe. So Earth's field is a very interesting thing. It does not stay. It looks a bit like a bar magnet, but it doesn't stay where it is. It does flip around. It moves. The poles wander around. Earth is not a It's not a static object. It's a dynamic object. And in one of the great questions as to why we have a magnetic field at all in the first place is still not completely well answered. And you can go to any people who study this and they can overwhelm you with words and phrases and well, obviously I know what I'm talking about. It's a geodynamo and it's the molten inside of the blood. And ultimately it really comes down to, I don't think people really quite understand. You can go and say, well, look, we've got a liquid core, which has iron in it and nickel in it. And those are two magnetic elements. And it's spinning around and we're spinning around. And, obviously there's a field made. Well, but that doesn't really tell you why the field is there. It just tells you that there is one. So, anyway, so that's kind of an interesting thing. The Earth's field is a very interesting physical object. It definitely does a lot of help for us. It is the cause of the aurora borealis, or the aurora australis if you're in the southern hemisphere. The magnetic field traps charged particles that are getting thrown at us by the sun, helps move them away from us so that we don't have to deal with them coming through the atmosphere and hitting us. At least most of them. So it's pretty helpful. We'll talk more about how that works later. But for right now, back to the idea of the poles. So if you look at two magnets, if I take two magnets and I take a bar magnet like this, which has a north pole and a south pole, and I take another bar magnet here, which has a north pole and a south pole, and I try to squeeze them together, you're going to find that these two poles repel each other. And you'll find the same thing with the souths. Okay. The interaction rule is exactly the same as it is for electricity. Like poles repel. So if you have two norths, two souths, they're trying to get away from each other. And if you've never played with refrigerator magnets, you should go do that because it's really fun to feel magnets repelling each other. It's kind of ethereal in some sense. You're trying to push these two things together and you have this kind of thing going and they don't really want to, and you kind of have to really push and it's quite fun. It's like there's some kind of jello that's telling them not to get together. However, if I have a north and a south, those are opposite poles and they will attract. Okay. So back to what we have going on here with Earth. I have a north pole of a magnet pointing to the north pole of Earth. Well, wait a minute. Didn't I just say that Like poles repel? Well, that's weird. Why is the north pole of a magnet in my compass pointing towards the north pole of Earth? That's a north attracted to a north. That's not right. Well, that's two different types of poles, uh, you're wondering. The north geographic pole is not a magnet. So the north pole of your compass is named north because it points north. Thus, the magnetic pole that is up here in the northern part of the hemisphere must be a south magnetic pole. And the north magnetic pole is down here because that's what's attracting the north part of your compass. It's really quite simple. The north pole of your compass is attracted to the north pole of Earth, where the south magnetic pole up in the northern hemisphere, because north attracts south, and the south is down in the north, and the north is in the south. So it's obvious. Alrighty. So, anyways, like I was saying, these things do flip around every now and again. And I think our last magnetic pole reversal was somewhere in the range of 500,000 or 700,000 years ago. They flip around on the average about, let me put it this way. It seems like we could be due for one at some point soon, in which case our magnets will all stop working, which would be pretty funny. All right, so there's that. Okay, that was not what I wanted. So let's undo. Okay, good. So let's go back this way. Okay, so all magnets are dipoles. Um, the the offshoot to that is that no magnet is a monopole. They're all dipoles. So we to this point have found no isolated magnetic poles by themselves. All right, so no magnetic pole exists by itself. In other words, if I break this bar magnet that I drew for you right here, notice I didn't label the pole on here. It doesn't really matter. You can't tell if it's just iron filings. You can't tell if it's what the direction of the field is. But if I break this thing here, suppose I've got a north here and a south here, right? If I break this thing in the middle, what I'm going to end up with is not a north side of the magnet and a south side of the magnet. That doesn't happen. What you do is you end up creating a north-south pair. No matter how much you break the magnet, this still happens. This is captured in Maxwell's third equation, which is kind of tentatively called the Gauss's law for magnetism, because ultimately it does the same thing as Gauss's law for electrical charges. Okay, back to electrical charges. You remember Gauss's law. For electrical charges, what we do is we go, oh, look, an electrical charge. And I go in here and I draw my Gaussian surface. Ding, 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 ding. And I look at the flux of the electric field through the surface. Okay. And I say, oh, the electric flux, that's related to the charge that's buried on the inside because there's a big flux through it. Okay. Well, if I go to try to do the same thing to a magnet, what this is telling me is that if I try to do something like this, here's the North Pole, all right, like this, you're gonna say, well, look, what's funny here is it seems like I've got some outwards pointing magnetic field lines, right? They're seeming to emanate from here. It seems like you could do the same thing. But no, you cannot, because inside the magnet, there is still magnetism, and all of the magnetism inside is going that way. So what it's telling you is that if you draw a Gaussian surface around a magnet, you will get zero flux. Okay, if you remember Gauss's third equation, I mean, gosh, not Gauss's third equation. Gauss had a lot. Well, if you remember the third Maxwell equation, Maxwell number 3 is that, oh, whoops. It's not that. Sorry, I just started the wrong one. It's the this one. There we go. Right? It's the flux of the B field, right? Through a closed surface is 0. And the reason the flux of a B field through a surface is 0 is because you have as much in as you have out, no matter what. So if you are interested, the thing I was about to write, which is the equivalent to this, is that the divergence of the B field is 0. You can also write it. It's very nicely written that way. Incidentally, B is the symbol for magnetic field. Units of the magnetic field typically for us will be Tesla. Oops, not the Telsa. All right, the Tesla, which is just a capital T. And you can find that from other things. We'll do that in a little while. So how big is a Tesla? Well, let me put it this way. Earth's field is very, very large in extent. And so it's kind of weak. So it is about, let's see, it's about 2,000, it's 1/2000th of a Tesla. No, that's not right. It's a 20,000th of a Tesla. Okay, so a Tesla is a pretty big. We have a magnet. We have 2 magnets in the stock. Oh, now we have 3. We just got one. We have 3 magnets in the stockroom whose fields are in the range of about a Tesla, or maybe 2. And those ones, let me tell you, if you get near those, you're kind of like going, oh boy, be careful. Because if you have another piece of iron near it, it's going to really hard. And so typically the problem with magnets is a pinch. It's a pinch injury because the piece of iron you're holding, here's the magnet, the piece of iron you're holding traps your finger. So it's just so strong that you can hurt yourself. So a Tesla is it's kind of like the magnetic equivalent of a Coulomb. It's a really big unit. Very often we will be speaking, as we did of capacitance, micro Tesla, milli Tesla, maybe nano Tesla. I'm not sure about the nano Tesla, but it's going to typically be knocked down. So B doesn't diverge through a closed surface. There's as much going in as there is going out. And that is a fundamental law. Now, that's not to say that these magnetic poles haven't been predicted. Back in the 1930s, a fellow by the name of Paul Dirac said that, gee, if we could find a magnetic pole, if these things did exist by themselves, that would explain why the electron has the charge that it does, which is pretty interesting. Unfortunately, we've never found one. So if you happen to trip over a magnetic monopole, this is known as the monopole problem. Then let me know, bring it to me, and I'll make sure you get the Nobel Prize in Physics next year. This year it was awarded to the folks who kind of showed and first predicted, that would be Penrose back in 65, the existence of black holes, and the group at UCLA who experimentally essentially sifted through the data and showed that the evidence is there that there's a black hole at the center of the galaxy, of Milky Way galaxy. So that was the Nobel Prize awarded this past for 2020. I think that was maybe a month ago, something like that. All right, so that's kind of the large scale talk. If you want to go into domains now, we're going to talk about magnetic domains. What does a magnet, if you start looking closely, what do magnets look like on the inside? Okay, we know that there's a north and a south. If I go back to my magnet here, let's see, I'm going to put the north over here this time, north-south. It turns out there's a very large, well, let me do this in red. All right. There's a very large magnetic dipole that exists inside the magnet, right? As well as the stuff that's coming out, kind of coming out from the North Pole. So what you do is you draw the field as coming out from the North Pole and into the South Pole. So the diagram of the field, which I forgot to mention above, is that the North Pole, the field leaves the North Pole and the field goes into the South Pole, at least around the outside. So the North Pole has kind of like the positive charge looking field of the positive side of the dipole, and the south is kind of like the negative side of the dipole. After that, there's basically no similarities. It's just that the fields are drawn the same. The dipole fields are drawn the same. So if I look in here, then I say, oh, okay, there's a magnet and there's a big effective magnetism inside the material. What if I took a material that was not a magnet, or maybe I took this thing and I busted the magnetism off it? So magnetism is such a fun thing. It's so crazy. Let me put it this way. Ultimately, our best models, and I shouldn't say true. I was going to say true understanding, but I don't even know if that's a valid thing to say here. Our best models of magnets must be quantum mechanical in nature, because magnetism is a relativistic quantum mechanical feature. So trying to fully give a description of a magnet in a classical sense, you're going to run into questions that you can't answer. Now, that's not to say that you should give up immediately when you ask a question here, but I'm just letting you know that our best description of a magnet is a quantum mechanical model. But nonetheless, that's what makes them so fun. Nonetheless, we will try to do our best here. So suppose that I have here, so that's a magnet, of course, on the top. This is now a piece of iron, which is not a magnet. Okay. Here is not a magnet. What does it look like on the inside? I don't know, probably something like this. It's divided up into random looking kind of things here. Looks kind of like spines on a leaf. Okay, kind of like this. And I drew a central kind of backbone. I guess I shouldn't have. Oh well. Well, not oh well. Let's go ahead and take some of that out. There. Okay, so what we've got here is it's basically the not magnet is divided into domains, and the magnetism is not gone. Okay, you don't destroy the magnetism, you destroy the overall structure of the magnetism. You destroy the long range order of the magnet, but you don't destroy the magnetism. The magnetism is still there. And if I were to draw the magnets, each of these domains is a tiny little magnet. It just so happens that they're pointing in random directions. like this. If I destroy the magnetism, the magnets are all there. It's just that you've jumbled them up into a smaller region, and then the magnets themselves are randomly oriented. Okay. And what that means is you have a collection of atoms, all who have similar magnetic properties, and they've all said, hey, everybody who thinks, that we all should be pointing that way, get over here. And if you think you should be pointed that way, go somewhere else. Okay. So they're all jumbled up. So the net magnetism is zero because they're randomly oriented. So one question is, how do you go from the top case to the bottom case? Well, you can do that. You can heat it up and pound it with a hammer, and right mechanically bash it. Um, you can heat it up, and it will unlock. It'll start them jiggling. It will unlock the domains, and then you cool it off, and then it'll kind of freeze. That's the wrong word, but it's a phase transition. It's kind of a fun thing. It freezes back into a randomized state. So that's kind of one of the takeaway points here, is that even the atoms themselves are magnets inside a magnetic material like an iron. If it's a magnet, then the magnetic atoms themselves uh, are magnets. All right, so stop here. We'll pick up in the next video.